Okay, so for today's lesson, we're going to be talking about relative motion. And this is sometimes referred to as the principle of Galileian relativity, named after Galileo Galilei, because he's the one who first sort of reasoned this. And of course, this is not to be confused with Einstein's idea of relativity, which we will get to at a later point in the course, coming up soon, actually. So we've looked at projectiles where the motion is influenced by gravity in the vertical direction, or it's accelerating at 9.8 meters per second squared, while the motion remains uniform in the horizontal direction, or its acceleration is zero, or there's no acceleration in the horizontal frame. And of course, this obeys Newton's first law, the law of inertia. When an object's motion remains uniform during our analysis, a physicist would say this object's frame of reference is an inertial one. So this is the horizontal frame of reference is an inertial frame, while the vertical frame of reference we'd say is a non-inertial frame. And the projectile's horizontal frame is considered inertial since the frame is stationary with respect to the Earth, but the object is moving through this stationary frame. But what if a frame of reference itself is moving? Can it still be considered inertial as long as the frame's motion is uniform? Well, let's consider traveling on a subway train. So once you're on a train, once it's stopped accelerating, leaving this station, or slowing down when it comes into the station, either one you're accelerating, you're either accelerating forward or backward. So the acceleration is zero because it's moving with constant velocity, and you start to walk or stand. Let's have you walking on the train. It feels much like you would moving or standing on the subway platform when it's moving in uniform motion. In fact, this is the principle of Galileian relativity, that the laws of motion are equivalent in all inertial frames. Now, as the subway starts accelerating, slowing down, or even speeding up or slowing down, it's not uncommon to stumble or fall, or at least feel like you're going to. And because of this difference, the cruising frame is considered an inertial frame. So this is inertial when the acceleration is zero, because it's not accelerating, because just like the projectile, its frame of reference was inertial in that it wasn't moving, its acceleration was zero, while the frame of reference for on the train, if the acceleration is zero, we'd consider that inertial as well. However, when it's slowing down or speeding up, we consider it non-inertial. So, however, to understand the overall motion of the train, for example, is seen as by someone on the ground, we need to combine the train's vector with that of your own. So, if the train is moving with this vector, and you are moving with this vector, your overall motion can be described by the resultant vector. That's longer than at least the train's vector, and yours as well. However, if you take the same train, oops, let's go with back to blue. If we go with the same train, moving with the same vector, and you are moving in the opposite direction, now your motion can be described by the train's vector, which is as it was before, and then you're moving with your vector, so your overall motion, the resultant vector, is shorter than the train's vector. So you're moving slower than the train. You're still moving forward if the train's moving faster than you, but you're moving slower than if you were walking forward along the train. In fact, you get an excellent sense of this if you've ever walked on an escalator. If you walk with the escalator, you move up or down faster, while walking against the escalator's motion, you go slower. and you can even remain motionless even though you're walking. And here's a little YouTube clip to show you what I mean. Okay, now it gets a little bit more complicated. Some would say more interesting if the person's motion is non-collinear with the frame's motion, meaning that it's not moving in the same dimension, either forward or backward, but some direction either off to the side or at an angle. But of course, with our understanding of vectors and employing the right mathematical tools, we can analyze these situations where the frame of reference is moving, yet still is an inertial frame, or at least we'll limit our discussions to inertial frames. So, for an example, let's look at number 2 on page 78 of the text. We've got in this example, we've got a boy and a girl are racing their canoes across a 500-meter wide river to a location that's due north of their starting point. Now, both young people can paddle their canoes at a velocity of 3 meters per second if the water was still, but in this case, the water is moving. The boy paddles in a northerly direction and lets the water carry him. So he's aiming north, but the water carries him to the west. While the girl aims her canoe slightly upstream, so she's aiming to the east. Upstream is against the current slightly, so she aims slightly upstream so that her canoe travels directly north as she paddles. Now, if the current in the river is 0.5 meters per second west, we're going to look at there's 4 parts, I think, to this question. We'll look at part A. But before we get there, I've taken the liberty of drawing the vector diagrams for the two situations. So we've got the boy's vector diagram on the left of this diagram, and the girl's vector diagram is on the east, or on the right. So now notice the subscripts. I've got the velocity of the girl with respect to the water, the girl with respect to Earth, and the water with respect to Earth, which is common to both. They both have the same velocity with respect to the Earth, whereas the boy's on the left is the velocity of the boy with respect to Earth, or v sub BE, and then v sub BW is the boy with respect to the water. But the difference is the subscript B refers to the boy's situation, whereas the subscript G refers to the girl's situation. So for part A, it says they want to know what the girl's heading is. Well, basically what they're saying is, what direction does she have to aim this angle theta? We'll call it theta sub G. So what angle does she have to head so that she ends up going directly north? Well, we know that her speed, her velocity, or that hypotenuse of that triangle, that VGW, because we know that with respect to the water, she can travel at 3 meters per second. We also know that the opposite side of that right triangle, the velocity of the water with respect to the Earth. Normally we use ground, but because I've got girl and ground, it's the subscripts would get confusing, so I'm just going to use Earth instead of ground. So the velocity of the water with respect to the Earth is 0.5 meters per second, and we're only going to worry about the speeds because we've got the directions set there in terms of the vector diagram, and we're only worried about the magnitudes in order to get at this. So we want to find the theta G based on this diagram. Well, we know that sine of that theta is just the opposite over hypotenuse, which we have, which is V WE over V sub W or GW. So theta is just the inverse sine of that. So I'm just going to plug in the value. So we've got the inverse sine of 0.5 meters per second all over 3 meters per second. And notice that our units will simplify because we have to, whenever we deal with a ratio, sine functions only work with ratios. It has to be dimensionless. And we end up getting a value for the angle. She's got a head sort of at 9.6 degrees east of north. So therefore the girl must aim with a heading of north 9.6 degrees east. And that's our solution to part A. So for part B, it's asking the time it takes for each person to reach the opposite shore. Now, in the case of the boy, he's going to reach the opposite shore, but he's going to be downstream a little bit. The girl is going to head upstream so that she heads directly across. But either way, the distance that's across the river, directly across the river, is, we'll call it delta dy. It's the same for both, and they're both 500 meters. In the boy's case, let's analyze the boy's case because it's a little bit simpler. He's also, so we'll look at his velocity in the y direction, which is just his velocity with respect to the water, which is going to be 500 or 3 meters per second. So if we want to find the time that it takes for him to get across across in the y direction, it's just going to be the delta dy over the velocity of the boy with respect to the water, which is in that y direction. So we get 500 meters divided by 3 meters per second, and it ends up taking the boy 167 seconds to cross the river. In the girl's case, though, it's slightly different because she's actually heading slightly east, but she'll end up going directly north. So we want to find her velocity in the y direction. Is just going to be that v sub ge in the vector diagram there, which if we use Pythagoras and rearrange it, if we square that value, it's going to be her velocity with respect to the water, which we know, all squared, minus the velocity of the water with respect to the earth, all squared. And of course, if we take the square root of both sides, we end up with her velocity VGE, which is her y velocity. So this is going to be, we're going to get 3 meters per second, all squared, minus that 0.5 meters per second, all squared. And we're going to take the square root of that, and we end up with her velocity being, I get 2.96 meters per second. That's her in her y direction. So her time is going to be her delta dy, just like the boy, divided by her y velocity, which is this VGE. So that's going to be 500 meters again, divided by that 2.96 meters per second, and it's up taking the girl 167 seconds, which is 169 seconds. That's what I get, 169 seconds. So it takes her a couple minutes longer, but she's going to end up directly across the river, whereas the boy's going to end up down the river, and he's going to have to come back, which takes us to part C and D, which I don't have time to do here because we're going to run out of time. But if you need to, I suggest you attempt part C and part D. Strongly recommend it. If you have any difficulty, you know where to reach me. But if you've forgotten, I'm at oddjobman@gmail.com. And I will see you in the morning.